This is a video on the rate law. The rate law expresses the relationship of the rate of a reaction to the rate constant and the concentration of the reactants raised to some powers. We saw in the previous video that the rate constant was a constant that was used in order to be able to equate rate with concentration. Because we know there's a relationship between concentration and rate, we know that the two are not equal to each other, but the rate constant, or the rate law constant, allows us to cause them or make them equal to each other in terms of the rate is equal to the constant times the concentration of the reactants. Now, in that problem in which we were looking at the bromine and formic acid reaction, we saw that it was a direct relationship and that Br2 would be raised to what we call the first power because the rate was directly related to the concentration. That's not always true for every reaction. Sometimes the rate is related to the concentration, but it's not raised to the first power. It might be raised to the second power, or it might not be related to the concentration at all. For a reaction A with a coefficient of A plus B with a coefficient of B reacting form C with a coefficient of C and D with a coefficient of D, the rate law can be written as such. The rate is equal to K times the concentration of A raised to the X power times the concentration of B raised to the Y power. The reaction is X order in A. So whatever the value of X is for A, we call that the order of the reaction in A. So if X were to be equal to 1, the reaction is first order in A. If X were to be equal to 2, then the reaction is second order in A, and so on. The reaction is Yth order in B. So if the value of Y is 1, then we say that the reaction is first order in B. If it is 2, then we say it's second order in B. If we take the sum of the two orders, if we take the sum of the X and the Y, we get the overall order of the reaction. So if X is 1 and Y is 1, then this is second order overall. Or if X is 1 and Y is 2, let's say, then it's third order overall. Let's do an example in which we're going to find the values of X and Y for a particular reaction. Those values can only be determined experimentally. So we write the rate law as being the rate of this reaction is equal to the rate law constant K times the concentration of F raised to the X power times the concentration of the ClO2 raised to the Y power. The way we do this is we try to pick two experiments in which the concentration of one of the species stays the same and it is the concentration of the other species that changes. This way we can look at how the rate changes when the concentration changes. So what we've got are three different experiments in which we measure the concentration of F2, and the same three different experiments in which the concentration of ClO2 is measured, and the initial rate. In other words, the rate right at the instant the reaction begins. If we pick the first experiment and the third experiment, we see that the concentration of the ClO2 stays the same, but the concentration of the F2 changes. So, what happened to the concentration of the F2? Well, to go from 0.1 to 0.2, it doubled. To go from 0.1 to 0.2, what happened to the rates? The rate initially, when the concentration was 0.1, was 1.2 times 10 negative 3. And when we doubled the concentration, the rate is now 2.4 times 10 to the negative 3. So you can see, as we doubled the concentration, the rate also doubled. So if the rate does the same thing as the concentration, then the value of X has to be equal to 1. If we double F2, with ClO2 being constant, the rate doubles, and therefore the value of x has to be equal to 1, because the rate changes exactly the same way that the concentration changes. So the value of x naturally would be equal to 1. Then we pick other two experiments now in which the F2 concentration stays the same, but the ClO2 concentration changes. Now, if we look at the ClO2 concentration, it's 0.01 in one experiment and 0.04 in the second experiment. So we can see that this concentration is 4 times larger than this. And if we look at the rate, we see that this rate is 4.4 times larger than this rate. So when we quadrupled the concentration, the rate also quadrupled. So we quadrupled ClO2 with F2 remaining constant. The rate also quadrupled, so the rate is doing the same thing as the concentration, and therefore the value of y must also be equal to 1. So now the rate equation would be written as K times F2 concentration times the ClO2 concentration as such. So you don't need to actually put the values of 1 in there because it's understood that it's 1. Let's look at another problem. Before we do that, let's talk about a couple of things. First of all, rate laws are always determined experimentally. You can never determine the values of x and y by looking at the equation. Reaction order is always defined in terms of reactant, not product concentrations. So we always define the rate in terms of the reaction constant K times the concentration of the reactants. The order of the reactant is not related to the stoichiometric coefficient of the reactant in the balanced chemical equation. So for example, in the previous example that we just did, we saw that the rate was equal to K times the concentration of F2 times the concentration of ClO2. The coefficient in front of ClO2 is 2, but of course the value that for which the ClO2 concentration is raised to is not 2, it's actually 1. So those values of x and y do not correspond to the coefficients of the equation. Now let's try another example. Determine the rate law and calculate the rate constant for the following reaction from the following data. So there's the reaction. S2O8 2 negative ion reacts with 3 I negative ions to form 2SO4 2 negative ions and the I3 minus ion. Let's first find the rate law. Of course, the rate law is going to be equal to K times the concentration of S2O8 2 negative raised to the X power times the concentration of I minus raised to the Y power. We're going to take our time now. We're going to find, in the first part, what the values of x and y are. Once we find the values of x and y, we can determine what the actual value of K is. And so, again, let's pick two experiments in which two of the concentrations stayed the same, and for one of the substances, and the other two concentrations for the other substance changed. So, let's look at the first two. We can see that in the first two experiments, the concentration of the S2O8 2 negative stayed constant, but the concentration of the I minus changed. Well, we don't have to look at it from experiment 1 to experiment 2. We can look at it from experiment 2 to experiment 1, and we can see that 0.017 compared to 0.034. 0.034 is twice 0.017. And if we look at the rates, we see that the rate has also doubled. So the concentration doubled, the rate doubled. So if we double the concentration of I minus, the rate doubles between experiment 1 and experiment 2, and that must mean that the value of y is 1. Now, let's do the same thing for these two experiments. Here, the concentration of I stays the same, and now as we go from 2 to 3, we see that the concentration of S2O8 2 negative has doubled. And what happens to our rate? It also doubles. So when we double the S2O8 2 negative concentration, the rate also doubles between experiment 2 and experiment 3, and therefore the value of x is equal to 1. Now, both of these values, or both of these experiments, or both of these examples that we've seen, the values of x and the value of y turn out to be 1. But again, this is not always the case, and in class we'll do a few more examples, and we'll show you a slightly different way to determine what x and y are. It's not really different. It's only different in the sense is that it involves a calculation as opposed to just looking at the data. And so we're going to do really the same thing. We're just going to involve a calculation so that we can verify the numbers in cases where it's not easy to tell what has happened to the rate. Now, let's move on. The rate is equal to K now times S2O8 negative concentration raised to the first and the I minus concentration raised to the first. Now we'd like to solve the second part and find the value of K. Well, it's very simple. We're just going to pick any one of those three experiments. We'll plug in the rate, we'll plug in the concentration of S2O8 negative and raise it to the first power. We'll plug in the I minus concentration for that experiment raised to the first power, and we'll just solve for K. So K is going to be equal to the rate divided by the S2O8 negative concentration times the I minus concentration. So apparently they used the first experiment because the rate is 2.2 times 10 to the negative fourth moles per liter every second. The I minus concentration 0.034 and the S2O8 negative concentration written in here. So when we do the math, we get 0.081. Now, what happens here in order to get the units is that the molarity cancels here with one of the molarities here, let's say this one, and we go molarity on the bottom and seconds on the bottom. So the unit is 0.0, or the answer is 0.08, and moles per liter times second on the bottom, or moles per liter to the minus 1 power times seconds to the minus 1 power. So we can express this as 0.08 moles per liter to the minus 1 power times seconds to the minus 1 power. So we can draw the line, make a slash and put them underneath, or we can actually write this as m to the minus 1 and s to the minus 1. Unfortunately, the units of K change depending upon the number of reactants and also the value of x and y. There's a simple way to figure out what the concentration, or what the units for the rate law constant is. And the way to do that is this. The value of m, when you write it as m to the minus something, the exponent of minus x, we'll call it x. The exponent x, when we raise this m to minus x, is going to be equal to the total number of m's on the bottom minus 1. So since there are 2 m's here on the bottom, and we subtract 1, take 1 away, 2 minus 1 is 1, obviously. So this becomes m to the minus 1 power. And of course the time is just brought down, and it becomes m times s, right? 0.08 divided by m times s, or it's m to the minus 1, s to the minus 1. So to come up with the units for the rate law constant K, always take a look at the number of m's here on the bottom, count them up, subtract 1 from the total because you've got this 1 m at the top which is going to cancel out one of the m's down below. So count out the number of m's, right? And subtract 1 and take your m and raise it to the negative exponent of the number of m's minus the 1 on top, and bring the time down as s to the minus 1. And this concludes our lesson on rate laws. We'll talk more about this tomorrow. Have a good night.